Are we good? Yeah, good. So this is essentially the basis of my provocation. What I'm interested in talking to you about is adaptive transformation. Please bear with me. I have 100 slides to get through in 10 minutes, so that's 6 seconds a slide. So it's going to go fairly fast. And one of the reasons is because I've interjected my own talk with another talk. Simply because we're actually also working with Implenia in Winterthur on what should be the world's tallest mass timber building, which is called Rocket, out of the Rocket and Tigerli, which is a kind of little area. And we try to see this as the kind of anti-tower, the sort of tower that does more for the ground floor and the space around it than what a tower is usually critiqued for doing in the first place. But of course we have the relationship between mass timber and facades is very important because of course it's not typically fire on this scale of timber that is the problem, it's moisture. And we have to design in a way that is both flexible over time but also a way that allows you enough sort of control and play over the elements. So it's also interesting to note that this tower is unlike all of the other so-called mass timber towers insofar as the load-bearing structure, the core and the shell, they're all made of laminated veneer lumber. So it's actually a vertical load-bearing structure, which is also mass timber, and I'll get into that in a bit. But the ability to then fold that core, which is here, the floor plates which span between the cores and the outer grid structure, they're actually working as two tubes, one against another, and it's this relationship between those two tubes that makes the structure robust, especially in seismic zones, for example. And then, of course, the facade on top of that. I guess the cleverness in the architectural design was based on where you actually organize the vertical surfaces so that in the way that we plan the building, we can make these changes and flips, which not only creates play in the facade, but it allows you to have this sort of ability to change spatially over time. And then another sort of innovation behind that, which I'll get back to later in this discussion, is the question, well, okay, mass timber is expensive or seems to be expensive to the industry. How do you relate that back to actual value, return on investment? How do you build a business case around it? And so we've built a kind of system that allows you to look at the design variations of what could possibly be built, analyze them on a series of baseline volumetric and sometimes like floor plate analytics, and work out even where things change in value over time, how you could create a building return on investment which takes in the design and materiality of the project, but also the, let's say, the design decisions, what you're putting where in the space, and also especially looking at design for adaptability or transformation over time, because we know the world is shifting in terms of its demands, and buildings get demolished not for the fact that they are not able to stand up anymore, but because of market forces. So to avoid this kind of thing, and of course a general collapse in the economy is almost symbolized by the general collapse of a building. So just looking into embodied carbon, of course, it's the relationship between it and its typical concrete counterpart is represented here in terms of proportionality. And of course, it's because there is embodied carbon, sequestered carbon in the timber, it allows us to see this like overall drop beyond the baseline goals of RIBA sustainable outcomes. Just looking, I have to shout out to Andrea Frangi, who's the chief engineer behind this and researcher and professor at ETH. And they've done a lot of work to look at how these binding systems can work so that the internal core and the external frame are able to work against each other. And they have to, of course, bear moment because shear force is carried by these two layers as well. There's a typical question about impact, vibration, flanking, that sort of thing in the acoustic realm, and that's also being studied. And part of the answer to that is the composition of the floors, which are both using concrete overlay on top as a compression article and timber on the bottom, which creates this stiffness, but actually, as you can see, when you apply massive forces such as seismic forces, there's a lot of toughness and flexibility in the system as well. A typical question is always about fire, and of course in this case Andrea is talking about the idea of charring becoming a protective layer, which I guess in this room you're all quite familiar with. He was also saying that you're able to rebuild that structural surface after a fire, so it's not a death knell to the structure of a building to have a fire. It can be rebuilt in layers to re-establish that capacity. So that's like really quick, but I just thought I'd put that out there because it's a mass timber event. But my main provocation is actually about adaptive transformation and the potential of mass timber in this realm. And I think we have a lot to talk about because I think you've got a lot of skills that we could possibly use. But what am I talking about, first of all, in terms of adaptive transformation? A lot of people talk about renovation or adaptive reuse, and we find the most difficult area and the one that has the most potential is actually when there's a typological change. When a building has served its useful life in one typology and can't be renovated, what then happens to that building? Does it get demolished? And so we have these sort of tropes in architecture that we talk about, like surgery, for example. If something was wrong with me, would you demolish me and start again? I hope not. So then there's the question, how do you treat a building in terms of the subtractions or additions that can be made? And how does that relate to the terms of risk versus reward? Well, in many building cases, the adaptive reuse or the adaptive transformations that have been done have more or less been applied to buildings that have some heritage overlay, where there's no choice but to transform. But what we're interested in is the typological standard, the boring buildings, the unimportant buildings, because that usually represents the majority of the market. So how do you take these boring buildings and start to use their native properties to create something that has a design value that is better than what you would have if you had a blank slate? And of course, if you were able to read that quote, our obligations as architects and designers are to understand what qualities exist that we can leverage upon. So there's many different ways of doing it, and I'm continuing with the sort of medical surgery trope, but in this building here it's interesting because this was a mechanical issue. It wasn't necessarily a structural issue. It's a library where the mechanical services were not fit to work between the floor to ceiling heights, and we plugged in this separate mechanical building to allow it to continue as life as a library, but we also used it to supplement the spaces that were not possible inside. It's a kind of life support system approach. And to get back down to Greg's favorite topic, what is this really about? Well, there are some fantastic and irreplaceable features of mass timber that are hard to supplement with others. Of course, there's steel, which is also lightweight, but there's a range of factors that I think it's going to be more interesting for mass timber than a steel product in the same circumstance. And I'll talk through that in a little bit. So why adaptive transformation? Well, because of this. Because the first insight that we could talk about is that there are dying typologies. It's not just that there are shifts in the building industry, but they're actually affecting, especially in America, Seattle, San Francisco, and north in Canada, and Calgary and Edmonton. Office buildings are starting to become obsolete. One of the background reasons for this is, of course, COVID, but another one is that there's this situation where global economics took a turn. And this is a picture that I quite like because it's quite clear that there's only one person in the room who has no idea what's going on. But it was the point at which Bill Clinton signed away the Glass-Steagall Act, which was a restriction on banks to essentially invent money. And this creates this exacerbation, if you like, of the boom-bust cycle in architecture and building industry and design, global economics generally. So this is a graph that pretty much talks about how every tallest building in the world was either built just preceding or during a major economic crisis, a symbol of the sort of boom-bust economy that we're experiencing in greater amplitudes now. So for that, what's the relationship between macroeconomics and lifespan dropping in buildings? Well, part of that is the idea that risk is being divested from the industrial sector onto individuals. We have more, in America this year, we have more freelancers than paid professionals, full-time contracted professionals, and the inability for companies to lease over the long term, or the needs of flexibility around the workforce, mean that there is dropping lease length and more pressure on the market to change the way that the architecture performs according to the market demands. And so you've got the situation now where the average building now lasts 50 years, commercial building, and is engineered to last 500 years. Maintenance included, of course. And that's reflecting, that relationship is reflecting on whole cities and whole typologies. So many situations occur now where it becomes unreasonable to even build a certain typology in certain spaces anymore. And of course, what does that relationship have to do with embodied carbon? As a lifespan shortens, the proportion of embodied carbon goes up. So again, back to mass timber, if you're building with lower embodied carbon, that's a general plus. But if you can save a building's lifespan, it's even better. And it's not just carbon. It's really the environmental catastrophe that's being created by the building industry is partly due to physical waste and the extractive nature of what building new is in the first place, where the money is being put into extraction rather than local labor. And I'll look into that a little bit further. So how might we establish an assessment toolkit to determine how existing building types might convert? Okay, so that's task number one for you guys, any of you guys who are attending the hackathon over this weekend. What we want to do is mirror the concept of material circularity in the building system. So to go from utilizing better to maintaining and repairing, and the first step is transformation before you harvest materials, before you recycle, and before you burn for energy. And the last two steps are what we're focused in most on the industry right now. So the design assessment toolkit, as a provocation, might look at the idea of fitness analysis. How might any building convert to another typology regardless of what that typology is? How do you feed the understanding of an AI so that when you present a building, it can give you a fitness test against different typological outcomes which are a change from its current state? And can that create a playbook? So that's something that we're working on at Schmidt Lassen as a research approach. Insight number two, transformation is becoming more desirable politically especially, but the business case is difficult to quantify. And that's because actually we're not very good as an industry at understanding what the cost of transformation are going to be. And I'll look into that in a second. But starting with the political desirability, if we understand that UNEP are saying, okay, by 2050, 80% of the buildings that are going to be there in 2050 are already built, then we have a real issue about how we even deal with, let's say, operating carbon, how buildings actually perform. So if you say 20% are built until 2050, new, it only really represents a fraction of the operating carbon because of the increase in performance goals of building codes. So if we were to reduce this by 50%, that really only leads to a small gain on the overall story of the way a city performs. Whereas if we instead improve the existing buildings by 50%, that's a massive win for the city, right? So, come on. So in that case, it's becoming, it was unaware, the politicians were completely unaware of the situation maybe 5 years ago, and now it's the hottest topic, and it's why WLCA is coming in as a real focus, and it's starting to influence the building code. And there are now many areas like Brussels, parts of Norway, parts of Denmark, that are looking to give incentives for adaptive transformation. So how do we then create a better picture of risks and returns? Because if it's about risk, then our job as an industry is how do we tackle that comparative difference in risk of new build versus transformation? And part of that is based on an understanding of what an ROI is and how it's predicted even before a brief comes out. Normally, a developer or a funder, let's say, would go to a real estate agent and they would say, well, how much per square meter would I get for this typology in location A? And that's the basis of return on investment is the basis of investment. But what is missing here in this relationship between real estate consultants and investment, how much could I get, can you do it, yes or no, is actually design. And when we look at the idea of getting into the strategic level of modeling options, then we can start to build design quality into the ROI features of the come on, play into the funding of the design process itself and how much you're willing to invest in the design of the transformation, what you're going to do. So what we're trying to do is build a system whereby this relationship between design quality and return on investment is clear to the investors. And finally, how to make transformation more attractive than demolition and rebuild. And so the second last insight, is that the building industry is educated for new build, but this creates an uneven playing field. And let's say you want to, demolish and build something self-similar in terms of the amount of square meters that you put in place, versus maybe transforming it. So you consider a standard office tower. Well, first of all, you could say, okay, most of the structure is there, most of the materials there, it should be cheaper. But then you get the situation that in our industry, it's very hard to estimate construction labor, time and cost, and these sorts of overruns that occur on site. Because we're using, in new build, we're going from the ground up using highly CAD, let's say BIM-influenced scheduling systems and very clear methods of construction. And we're back in the mid-1900s where everybody goes in with their bits of concrete and drywall and everything's done very manually in that process. So it's very hard to estimate. And labor availability and costs go up and down. So if your margin of error ever supplants the profit margin, even if you should be able to make more money in this situation, you'll go for this. So how do we do this? How do we reduce the margin of error in transformation? And I would say, okay, on top of that, as you've seen, how do you look at the design modeling situation and look at that in terms of ROI in the first place, what you could actually predict to get back in return for your investment? So this relates to modeling. How do we create tools that help us model the costs of transformation? And so when you look into what is the basis of a cost, the basis of the cost basis of a building, you can see that, of course, there is material cost and labor cost in both, but the proportion is more or less flipped. We understand that in transformation, the majority of the cost is in labor. But because we don't utilize off-site manufacture, because we don't have any systems in architectural design of actually modeling the process to deal with existing structures, then we don't have this ability to reduce the labor component of a transformation, and that's what we're working on at the moment. That's what we believe we can build to transform the market, because not only does it create a difference in profitability, but it also creates more of a narrow risk profile, which is the thing that is holding back transformation right now. So 3 parts need to be connected together: scan to BIM, construction simulation, and offsite manufacture for transformation. And that's why I want to talk to you. So in order to move forward with adaptive transformation, it's actually these 3 parts that we could tackle separately or together, but any win in any of these parts will make a sea change in the outcome of buildings demolished and saved. So this is the thing that I'm not going to explain, but how we're working through the process. And finally, the case for mass timber, which is the part you've been waiting for all this time. It's finally here. And that's simply this, and it's no more than this slide, really. It's the idea that there's a potential for mass customization, not just with big manufacturers, but with small manufacturers. There's the lightness and handling which make timber something which is unparalleled in a way, which is why perhaps you do your tricky stuff in timber. And thirdly, it's the concern of adaptability. If you're using mass timber, then it has very workable methods of being readapted in future when the market shifts again and the change has to be made once again. So here's a project that we recently won. We haven't started building it yet, but it's on its way. And it starts with the notion that we were given a site where the client really wanted us to tear the whole thing down and build 2 towers. And we said, okay, but actually one of them doesn't have very good structural basis for this kind of volume, and another one does. And despite the fact that the client hated this building more, we managed to save it. So we start with the adaptation. We add mass timber, and the interesting thing is it's not just building on top, but building within, and that requires a scan to BIM process where you really know your relationships between existing and future geometries. Then there's the idea that, okay, this side was also closer to bedrock, so we're reusing the materials there and going to the 3rd level of circularity on that side and the 2nd level of circularity on that side. And the notion that we kind of save the facade by existing facade by adapting it and mirroring it, if you like, in the facade that the client actually did like. So just a transformation there rather than a total rip out and reinstall. And you can see that when you use mass timber, even if you're creating more space, you get an experiential quality that you wouldn't otherwise have with a standard construction system. Material reuse, and final slide. And that's it. If you are interested in getting in touch, that will go straight into your phone as a contact, and then you can contact me. Thank you.
Thank you.